Okay. So, welcome to the course of perception algorithm. Last lecture I told you about the multi-target tracking. So, in this lecture what I will do, I will take some the steps, basic steps of multi-target tracking, and then we will straight away jump to the association, nearest neighborhood association. So, if I told that first, whenever all the measurements are coming, they are all valid targets or valid clusters, number 1. Then we will create a small neighborhood around the targets, all the previously formed targets or clusters. They are called the elliptical neighborhood is called gate, track gate. It could be position gate, it could be velocity gate separately, and I will try to qualify all the next scan measurements to the gate. If the measurement is fallen into the gate, then it will say it is gated or it is not non-gated. Non-gated means I will assume that they are on fall. So, they are false alarms. So, all the gated measurements, there could be now ambiguity. Some measurements could fall in multiple track gates, or some 2 track gates share a common measurements. Either thing can happen. Some measurement do not fall in any of the track gate. So, that means they could be a new target. Some tracks previously generated tracks didn't find any measurement. So, that means the target either it is a misdetection or target is dead if it is prolonged. So, this could be 3 possible combination out of your gating 1, 2, 3. Okay. Next part what we will do is called now measurement to track assignment. Measurement to track assignment. My handwriting is not so great, but at least you can understand. Measurement to track assignment. So, I got now once I execute this part, I will know which measurement belongs to which target. It could be one measurement to one target, it could be one measurement or multiple measurement to one target, or it could be all possible combination. These 3 we will be taking. So, here there are 3 methods: nearest neighborhood methods, probabilistic data association method, it is a different kind of filtering, Kalman filter only an extended version. Another one is multi-hypothesis tracking. This is done. Once I get this step, then I will do filtering. Once the filter is updated, then I will maintain my, so here to here, I will maintain my track file. Okay. I will write the data into my track file, and in between I will perform this track deletion, track merging, 2 or maximum number of tracks, maximum number of new tracks, all this my constraints I will keep, so that my tracks does not get infinitely large. Okay. So, this is all the flowchart is all about. So, today in the first class what we will be telling you SNN. Okay. What is the philosophy of SNN? This is my last thing. So, what is the philosophy of SNN? SNN means 1:1, one track, one measurement, one track, one measurement. So, if your track I say TI, so TI will be linked 1 MI means measurement. This is called NN. It could be now do it 2 ways, one is called suboptimal nearest neighbor, one is called global nearest neighbor, we will talk about it. Second is called probabilistic data association. This fellow says TI or say T1, let me say go to this example. So, here you say T1 got M1 and M2. Okay. So, T1 I will make a function of M1 and M2. T2 I will make function of M2 and M3. T3 I will make function of M1, M3. Okay. And T4 I make function of only M1. This is called probability. So, all the link whichever is gated I will use all the measurements and I will give some weightage probability. This much weightage I will give this x% weightage I will give this 1 minus x% probability I will assign for M2. like this. I will solve it. We will talk multiple classes to how the PDF is concerned. Last is your MHT. Already I told. Sorry. All the possible pairs as per my gating cycle. I will keep all the possible pairs, and after that I will maintain which pairs are consistent and which pairs are not consistent. Consistent means they get uniform update for each and every scan, that means it is consistent. If it is not within 2 or 3 cycles, if it is then thing, then I will delete it. The problem with MHT is called multi-hypothesis. PDF and NN, they are actually single hypothesis. Okay. So, they are called actually single hypothesis method. So, that is the difference between PDA and this thing. So, because every scan I get one measurement, one track. Every scan, one measurement, one track. So, this is a scan K, scan K, scan K, scan K, scan K result. MHT is not like that. MHT means I will combine all the pairs, I will keep the pairs in my heap or in my memory. Okay, I will write it somewhere, and I will see after 3 cycle, I will see which pairs getting consistent update, and then I will go back to my 3 step back and say, guys, you have a consistency, so you are my confirm track, you are my perfect candidate, and which does not have consistency, that will automatically delete. So, I will reduce the score in such a way that I will delete it. So, this is the, in very basic English term, this is called the multi-hypothesis tracking. We will talk in details, but this is very important to understand in tracking. So, these are the different methods which are there as of now in literature, because tracking literature is started almost 1970. I was not born that time. So, from 1970 people have started tracking. It is, and these methods are well kind of established in kind of in different radar or different UIR or any kind of industry, autonomous system basically, autonomous industries. So, this course, the purpose of this course is that we have 50 years back methods are already available, and we would like to kind of know the basics of it. There are multiple versions are available, also new versions are getting formed, and still this IEEE signal processing or IEEE aerospace electronic systems or even IEEE TVT, vehicular technology and all, they have many papers in tracking. Okay. With this, now I will tell the different kind of target tracking things. So, one is single hypothesis. So, NN and PDA are single hypothesis, multi hypothesis I told. So, NN, so what are the different things? Nearest neighbor we will cover. And nearest neighbor, two types, one is called suboptimal nearest neighbor. So, it will take the nearest candidate, as you say, it is just nearest candidate. Another one will solve an optimization routine, simply an optimal assignment routine, either JVC or Mooncrest. We will talk only about Mooncrest, we will solve multiple examples also to do how this thing is Mooncrest's algorithm is working. And then your probabilistic data association. So, probabilistic data association means one is too many, I just wrote it already. Okay. There are certain variants, nearest neighbor probability association, K nearest neighbor method. So, these are actually, there are certain problem with this original PDA, and there is something called MLPDA also. Maximum likelihood, it is not written here, maybe I can write it here, MLPDA, maximum likelihood probability. This is a patented algorithm from Barsalam and Kirubarajan, and this is used for many kind of Raytheon radar in early 90s. Okay. So, this is all kind of derived from the probabilistic data association with multiple modifications. Okay. And MHT, you have two approaches, one is actually your track oriented approach, another one is called hypothesis oriented approach or target oriented approach. So, we will be only covering the track oriented approach. Okay. So, this is the thing, gating I already told multiple times in my lecture. So, say this is your track, you create a small neighborhood, neighborhood means you just create a norm of innovation with the incoming measurement. The next scan you have measurements are coming. So, you are in your estimated space at t equal to k minus 1, you go using your Markovian dynamics or your state transition matrix, you go to a predicted space at t equal to k, you got the measurement at t equal to k, and you form the innovation and normalized of innovation. So, this is called a statistical distance. So, this is called statistical distance. Sometimes it is known as Mahalanobis, or if you know the statistics, your courses, this word is very famous. This is from famous statistician Mahalanobis. This is called Mahalanobis distance. Okay. So, and now you, and this size you fixed it, this is called your gate size. I already told how to select the gate size in my earlier lecture, and you try to fall this everything in a single gate. So, now here you see your track, you have M1, M2, M3, all three are fallen within the one gate. Now, you can see the distances D1, D2, D3. Which one is least? You can see the figure D3 is the least. Okay. So, suboptimal nearest neighbor will say, guys, I want my D3, this is my measurement. So, D3 will get updated with TI, right. This fellow will say, a PDF will say, well, I have 3 stars M1, M2, M3 and D1, D2, D3. I will use all this thing. So, D3 is just a distance. So, how the distance is calculated? You know the norm of innovation. So, any norm function is calculated is transpose inverse, multiple times I am writing it. The norm function is calculated. So, this is the norm. Now, if you plot it into your Gaussian distribution, you get some probability. So, PDA actually weight these measurements to your association probability. So, what is your association probability? 1 by square root 2 pi into sorry, not 2 pi, into actually your sigma. Sigma means actually your square root of your Sk into your e to the power transpose Sk inverse. So, this is your actually your Gaussian typical bell shaped curve. So, it will give you association probability. So, it will be weighted, each and every measurements which will be weighted. So, obviously, the nearest one will get the maximum weight and the furthest one will get lesser weight, and your probably this distribution is kind of normalized. Okay. So, it will be this is a very basic philosophy, but actually PDA something else is also there that we will talk when we have in a PDA class, PDA lecture. Okay. So, this is also actually the gating. So, you are doing based on your Mahalanobis. So, with this Mahalanobis, now I will come to the suboptimal nearest neighbor and global nearest neighborhood problem. So, let us take this is after gating. Once you have done gating, you get say this kind of TMCR matrix. So, TMCR matrix means these are all statistical distance. So, your norm of ZK residual is the secondary norm. Okay. Once you do this, so you have T1, T2, T3, T4, P1, T2, T4, which are non-gated. That means, those measurements are non-gated, we replace them a larger value. 1000 is just a number, it could be you can write it 10,000, 5,000, 1 lakh, I do not care, 1 to the power 10 to the power 10 also I do not care, some large number I will put it. So, that means, this signifies that these fellows are not linked to any kind of incoming targets. So, M6 is a new measurement or new target, since it is not linked to any of the previous target or old target, and T4 this fellow is also does not link to any measurement. So, that means, either this is a misdetection for T4 or it could be dead if it is prolonged, or if it is continuously it is not getting any measurement. I have to then delete the T4 after certain scan or certain interval, okay, 10 cycle, 5 cycle as per your choice, and remaining your T1, T2, T3, M1, M2, M3, M4, M5 as well. With all this thing, now I have to solve a assignment problem, or if I use the global nearest neighborhood. If I use a suboptimal nearest neighborhood, I will pick the minimum, very much minimum. So, what is the minimum distance? T1 M1. So, that means, this measurement is actually closer to my predicted track. So, T1 M1 is 1. So, I will update this. So, yellow color mark is like this. T2 is M2, this is the least. T3 is M5 because all other are larger numbers, it is M5. So, I get my 1:1 pair, write your Kalman filter, no problem. Suboptimal nearest neighbor is good, but it works also in a different example it works, but there are issues that it might generate lot of false tracks also, because it is a very crude level of doing it. So, to remove this kind of crudeness and all, you need to solve, you need to do this thing by optimizing and optimizing this assignment matrix. So, it is basically you need to solve a optimal assignment problem. So, this is called a TMCR matrix, and the optimal assignment algorithm could be Hungarian Munkres with the famous mathematician John Munkres, American mathematician, and there is another method which is equivalent, is called JVC, Jonker, Volgin and Castanon. So, JVC we won't talk, it is not very popular also, but in some places in Raytheon and industry people are using JVC than Munkres. But Munkres is well enough, well good. I do not see a problem, at least in my experience, I have not seen much problem using Munkres. It gives good result also. So, you are actually solving an optimization problem. So, what is the optimization problem? This is your cost matrix. So, this is a TMCR means track to measurement correlation matrix. So, these are all cost functions. So, these are all actually your Mahalanobis distance, Mahalanobis distance. So, with this your Mahalanobis distance Cij is your cost into some probability, say assume a probability, so zeta ij. So, such that this probability with all respect to your for all the incoming measurements is say is equal to 1, and with this it is with all the incoming tracks it is a 1. So, you target constant, if they are linked, you have it is a binary Boolean you can identify, and you will not say is the probability, it is you can identify as a Boolean number. So, it is a Boolean number whether you are linked or you are not linked. If you are linked, you are 1, if you are not linked, you are 0. Okay. So, that means 1:1 linking. So, see the way optimization is done. So, if it is a 1:1 linking, then only sigma ij for all over the measurement or all over the tracks it will be 1, right, because it is a 1:1 linking. If it is a 1:1 linking, then it will be, it cannot be 1. So, that means 1:1 linking is expressed mathematically using these two cost function. So, if it is linked 1, if it is not linked, it is 0. I am sorry, I mentioned it is a probability, it is not a probability, it is a Boolean identifier, just to express this measurement in a or this optimization in a mathematical way. Now, you solve your Munkres, Hungarian Munkres. We will take some example also how the Hungarian Munkres is solved. So, first step is called it is a similar, those who have done the courses of optimal assignment, they are aware of it. So, something called row reduction. For each row in the matrix, identify the smallest element and subtract it from the element in that row. This is a numerical algorithm, you know. Then you have to do similarly a thing for each column also. Pick the minimum and subtract it from that thing. Then you mask all the 0 and get the using the minimum number of horizontal and vertical lines. Then you check optimality check. If the number of covering line equals to n, then optimal assignment is possible. Your algorithm is over. If not, then you have to go for next step. So, you have to adjust this matrix, and remember one thing, Hungarian Munkres originally developed for a square matrix, but here in this case it is an extended version because you have a rectangular matrix. You cannot have a square matrix all the time. It could be square, good, but it could be rectangular also. So, when you write, because there will be an assignment to write a small MATLAB or any Python code for a Hungarian Munkres algorithm, and where you will be given a matrix and you need to generate kind of the output 1:1 pair out of it from your function. Okay. Then you have to determine the smallest entry which is not covered by any line, subtract, and then, so these are all some mathematical steps. I will take an example and this will be cleared. So, let us say this 2D array. So, this is just a travelling salesman problem I took, nothing to do with tracking. So, say this is your cost function, and what is the minimum? So, step 1 what it says, minimum of every row. So, this is minimum in this row, this is minimum in this row, this fellow is minimum in this row. Okay. So, you got zeros in first column. Now, subtract the minimum of every column. So, what is the minimum of every column? This is 0, I can't, 0 minus 0 does not matter. So, here it is 500. So, 0 2500 are subtracted from column 1 to 3. So, here it is 500, because 0 I will mask it, 0 I will not consider. So, 500 to 2000 minus 500 I have to do, and here 1000 minus this thing I have to do. Okay. So, once I do, then I cover the 0 for the horizontal and vertical lines. Then we got this thing, we subtract the smallest uncovered entry for all the rows, smallest is 500, then we got it like this. Then again step 6 and step 7 when we do. So, finally, we get an 1:1 pair. So, this one and this one, and optimal cost is this. Okay. So, this is just a numerical algorithm with which how the Mooncrest algorithm actually works. Okay. So, there are so this is a numerical assignment, because this is the same as, I won't go into details because this is already covered in your operational research or optimization classes. So, I won't go into details of this Mooncrest. So, this, but there will be a problem for this to in this thing. With this now, let me come to the direct tracking. So, nearest neighborhood, what is there? So, you have state estimate, you do the prediction, you come the measurement prediction also fine, then you calculate your innovation, you calculate your Mahalanobis, then you say that whether it is within your gate size or not. If it is fallen within the gate size, yes, it is gated, computed innovation, and you do the measurement update and you complete out. Similarly, for your state covariance matrix also. Okay. So, this is actually all about the nearest neighborhood association algorithm. In my subsequent lecture, what I will do, I will take two problems which is very important. One will be for a single track in a vehicle collision avoidance system. If you remember in my earlier class on Kalman filter, the same problem in presence of clutter, single target in presence of clutter I will take. Another problem I will take with single this thing with multiple targets in presence of clutter, and how the nearest neighborhood association algorithm actually behaves, that we will be dealing. So, this is the fundamental of nearest neighborhood association. Okay. So, with this now I would like to close this lecture. Thank you for your time. So, we will come in the next lecture with the problem statement to understand more about the nearest neighborhood association. Thank you for your time.